In this video, I'm going to be talking about evidence for continental drift. So in previous videos, I talked about Wegener and his theory on continental drift. So just to recap, the German scientist Alfred Wegener proposed that hundreds of millions of years ago, all the 7 continents of the world were once connected in this supercontinent called Pangaea or Pangaea. And as a result of plate tectonics, Pangaea broke apart and the 7 continents were formed. But Wegener didn't have any physical proof of this. Okay, it was only a theory, hence the theory of continental drift. It wasn't until instrumentation and sophisticated technology started coming out that evidence started mounting to support Wegener's claim, Wegener's theory. In particular, in around 1960, there was an American scientist named Harry Hess, and he proposed the idea of seafloor spreading to provide a physical mechanism for continental drift. And the idea goes like this. Let's suppose you have the ocean floor here. So I'm drawing this in a 2-dimensional way because I'm obviously limited, but it's just think of it as like a 3D image. Let's suppose I've got like an island here next to it. Now, what Hess found and what the US Navy actually found, they actually mapped the ocean floor during World War II using sophisticated equipment, and they found there was this long sort of continuous underwater mountain range called a mid-ocean ridge. Okay, a ridge can be thought of as like a mountain. Okay, a massive. For hundreds and hundreds of k's, it's like a underwater mountain range. And beneath this mid-ocean ridge, there's magma. So magma is this basically semi-solid. It's a semi-solid. It's like really hot sort of rock soup, if you wish, coming out from the mantle. So the mantle's beneath the crust. This is coming from beneath the crust. Magma's coming up through the earth, through the mid-ocean ridge. So it basically spews out. And as it comes out, it progressively cools. Now, if you recall, the mantle is much hotter than the crust. So the deeper you go down into the earth, the higher the temperature. So there's increasing temperature the deeper you go into the earth. And I should also mention along this the mid-ocean ridge, you'll find what are called rifts. A rift is another word for crack. And so when the magma cools, you'll get new crust. Okay, think of candle wax, for example. So when you melt candle wax, it's liquid. When it cools, it turns into a solid. Okay, so you get new crust forming. And so suppose you've got an island here, right? Some island, houses, trees, whatever. This new crust can actually subduct. Subduct means to sink. Subduct. Okay, when you have 2 plates, when you have 1 plate, so this island, let's say, consists of a continental, it's called continental crust. Okay, because it's sitting on a continental crust. It's a plate. When you've got a plate formed from the new crust moving to the right, it could sink. It could sink and form what's called here at the boundary. This is called a trench. All right, a trench is like a massive hole in the ground. Okay, it subducts. Okay, it sinks. It sinks beneath the continental crust because it's heavier. All right. Further evidence to support seafloor spreading is what's called magnetic stripping. It's a very simple idea. So magma actually contains magnetite. Magnetite's like a mineral, and magnetite contains iron. Right? Magnetite, think of them as like little particles found in magma. Now, iron is magnetic. And so why is this significant? Why is this really important? Well, because it basically tells us the history of the Earth. So if I scroll down here, if I redraw what I drew before, okay, let's suppose that's the ocean floor, mid-ocean ridge. So new crust being formed as a result of cooling magma. As the magnetite cools, it basically freezes. You can think of it as freezing, freezes its magnetic orientation. So think of, if I was to zoom into a piece of magnetite, I would see, let's say, hypothetically, a north and south, it's like a compass. Each magnetite's like a compass. And it basically tells us the orientation of Earth's magnetic field at that time. Let's say 100 million years ago. 100 million years ago, the Earth's magnetic field was, let's say, oriented as we know it as it is. North is pointing upwards, south pointing downwards. And then let's suppose, I don't know, 100 million years later, the magnetic field flipped, so south became north and north became south. Right? This is called reverse polarity. Okay, polarity is like direction, basically means direction. This is normal polarity. And so what you can then see is alternating bands of normal polarity and reverse polarity. So if I was to map out the magnetite, magnetic field orientation, I would see this. Okay, strips. So this, let's say, is a representation of the magnetic orientation of Earth. Okay, so let's suppose the ridge is here. You've got dark and white alternating bands. So let's suppose the dark bands represent normal polarity, so north, south, and the white bands represent reverse polarity, south, north. And so you have this alternating band of polarity. And so you've got a glimpse into Earth's past, into Earth's history, because you can basically determine when Earth's magnetic field flipped as a result of cooling magma. Okay, and the magnetite being, the magnetic orientation of the magnetite freezing. So very fascinating evidence to come out of Harry Hess's work.